All right. Hey, how are you doing? We're looking at Unit 7 Power Series today. Not Unit 7, Unit 10. Good grief. Sequences and Series, Lesson 7, Power Series, kind of Part 2. So we'll be able to represent certain functions as power series, as well as integrate and differentiate a power series, which is kind of crazy that you can integrate and differentiate these things. So recall if we have a series from 0 to infinity of r to the n, that this was a geometric series. Remember that ratio r. The sum of that series is given by this formula. This is the specific one when we start at 0. There's a slightly different form if you started at a number other than 0. And in order for it to converge, the absolute value of that ratio, that fraction, had to be less than 1. If I look at this quotient and this quotient, and I replace this r with an x, it now looks like this. So instead of it being a geometric series, now we think of it as a power series. And that power series is x to the n. Find power series representations of other functions. So what do I mean by that? We're going to prove that 1 over 1 minus 2x is equal to the series from 0 to infinity of 2 to the n, x to the n for x less than 1/2. This looks kind of wacky, but we're going to take this nice and slow. So if we look at 2x, we're going to replace the x with a 2x. So let me start at the beginning here. If I know that 1 over 1 minus x will become the series, the power series 0 to infinity, x to the n, and the absolute value of x is less than 1. Let's put all those things together. We're going to substitute 2x in place of the x that's over here. So 1 over 1 minus 2x would be n equals 0 to infinity. Again, replace the x with a 2x to the n. Replace this x with a 2x. Okay, so what did I do? I replaced x, whoops. I replaced x with 2x, and I replaced x with 2x, and x with 2x. Not bad. So let's clean this up a little bit. Series are nothing more than exponent rules. So n equals 0 to infinity, 2 to the n, x to the n. Now, the absolute value of 2x is less than 1. This 2 is always positive. You can actually pull that to the front of your absolute value. And we can divide both sides by 2. So the absolute value of x is less than 1/2. And now you have an absolute value inequality, which is exactly what I'm teaching my algebra classes right now. So here is how we went through the steps. We got 2 to the n, x to the n. We got absolute value of x is less than 1/2. Good job. So example 2, prove that 1 over 2 plus x squared is equal to the summation from 0 to infinity of negative 1 to the n, x to the 2n over 2 to the n plus 1. And for which x is this formula valid? So start out with that power series formula again. 1 over 1 minus x. That should be, or that's represented by the series 0 to infinity, x to the n, when the absolute value of x is less than 1. So we have to prove this situation that's going on in example 2. We need to have, instead of a 2 plus x squared in the front, we actually have to have a 1 minus x, or 1 minus u. So we need to do some rearranging. I'm going to use a different color green here. If I have 1 over 2 plus x squared, I'm going to factor out a 2. So this is 2 plus 1, 2 times 1 plus x squared over 2. Okay. The next thing I'm going to do is leave my 1/2 in the front and think of this as 1 over. This is going to look a little funny. 1 minus negative 1/2 x squared. Why did I do that? In fact, I lost the x here. Why did I make this minus a negative instead of a plus? The reason I did that, there's a plus here, but the formula has to be a negative. So I need this to be a negative here. Okay. So then we have to substitute negative 1/2 x squared in place of x. So this would be 1 over 1 minus x, right? In place of this x, we're putting that negative 1/2 x squared. So series n equals 0 to infinity, negative 1/2 x squared to the n. All right, so this is all about simplifying those exponents again. So let me get rid of this x. That's what I started to do before I had to pause. Negative 1/2 x squared, and this is what we're looking at. So put the n on everything. So the series from 0 to infinity, negative 1 to the n, pull that negative out as its own thing. A 1/2 to the n, and an x squared to the n. And then the rest of this is just simplifying exponents and seeing what things look like. So I'm going to come down here on this next line. N equals 0 to infinity, negative 1. I think I wrote that to the first, negative 1 to the n. 1 to the n on the top is still 1, so I don't even have to worry about that. That's just going to become 2 to the n in the denominator. And then in the numerator, if I have an exponent raised to an exponent, those just get multiplied. So this is x to the 2n. And if I look, I think I have exactly what we need. I think we're good if we replaced all of this. Now, I did have, and I see my notes have this 1/2 in here, and then I crossed off, and it looks like they really should be there. I have this 1/2 in the front, so that should still be in front of everything. Okay, this should be up here. So I thought I made a typo, but I really didn't. And then for which x is this formula valid, we actually have to put this negative 1/2 x squared in place of the x where we have the absolute value of x is less than 1. The absolute value makes everything positive, so you don't have to worry about it. So it's 1/2 x squared is less than 1. Factor out the 1/2 or pull out the 1/2. It's not really factoring. Is less than 1. Absolute value of x squared is less than 2 when I multiply on both sides. And then I can say that the absolute value of x, if I take the square root of both sides, is less than the square root of 2. So the radius where that converges, radius of convergence is that square root of 2, if that comes up. All right, good. A power series is differentiable within its interval of convergence, and we may differentiate and integrate as if it were a polynomial. Term by term differentiation and integration. Suppose that I have a power series given in that form, has a radius of convergence of r greater than 0, then f of x is differentiable on that interval, and its derivative and antiderivative may be computed term by term. More precisely, for x on that interval, we have the derivative of the series. You move the exponent to the front and subtract 1, or to integrate, just like we did before, you add 1 to the exponent and divide, where a can be any constant. That's really your plus c. The series have the same radius of convergence, r. So differentiating a power series, prove that 1 over x squared is equal to that whole expansion. All right, this is a little crazy, but let's see what you can do. So if I have, let's start with 1 over 1 minus x, which I know is equivalent to the power series. This is what we've been working with so far today, right? If I find the derivative of 1 over 1 minus x, that's really the derivative of 1 minus x to the negative 1. And if I use a chain rule, that would really be negative 1, 1 minus x to the negative 2 times another negative 1 by the chain rule. So this would be a positive 1 over 1 minus x squared, that quantity x squared. Well, that's what we've got here. So this is the derivative of a power series. All right, so if 1 over 1 minus x is equal to my original power series, n equals 0 to infinity of x to the n, which would be 1 plus x squared plus x cubed plus x to the fourth. So if you expand out that power series, you've got 1 plus x squared plus x to the third plus x to the fourth. Now, if I find the derivative of each one of these, well, what does that look like? So derive in all three versions. DERIVE, that doesn't look right today. So we already took the derivative of 1 over x, 1 over 1 minus x, and that's 1 over 1 minus x quantity squared. If you take the derivative of the middle one, well, by the rules we just had up above, we know that we bring n to the front, x to the n minus 1. And then if you take the derivative of each one of these, well, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. And if you look, that's exactly what we've got going on. Now it says for negative 1 to 1 over that interval. And that's what we have here. This is what my algebra class is doing. We're saying x is less than 1, and then x is greater than a negative 1. This becomes negative 1 is less than x, which is less than 1. So that's the same notation that's given here. Are we missing anything? I don't think so. Just keep in mind here, the radius of convergence, whatever the radius of convergence is for the original problem, that's where it's differentiable. And that's where the antiderivative may be calculated. All right, that's example 3. Okay, example 4, I think, is the last one that we have to deal with here. All right, example 4, prove that the inverse tangent of x is equal to that following series and then equal to that expanded form. So let's see what we've got here. If I start with the inverse tangent of x, and if I find the derivative of that, I know this is going way back, but if you pull out your golden ticket, the derivative of the inverse tangent of x is 1 over 1 plus x squared. Now, if I turn that into the form because I know I really need 1 over 1 minus x, that's what the power series has to be. This will be 1 over 1 minus negative x squared. Now, if I take this negative x squared, just like we did in the previous examples, and substitute it into the series formula, this is the series from n equals 0 to infinity of a negative x squared to the n. And then we have to break this apart. Remember all your exponent rules. So this is n equals 0 to infinity, negative 1 to the n, and an x squared to the n. So kind of keep going down here. N equals 0 to infinity, negative 1 to the n, x to the 2n. So now what we want to do is integrate this and see what we get. Because when I'm looking, this is fairly close to what we have going on here. It's not exactly there yet, but we're getting there. So let's integrate. So if I integrate this series, n equals 0. So if we integrate the series, -1 to the n, x to the 2n, right, we have to integrate that. What would it look like? Well, the -1 to the n stays the same. You integrate the x piece, that's your variable. So this would be x to the 2n plus 1 all over 2n plus 1. And then plus c on the end. I think our formula up above called it an a, but an a or a c. And that's what it looks like. To determine c, set x equal to 0. So the inverse tangent of 0 is equal to 0 plus c. So what am I doing? I'm setting this first piece equal to this. So if I put 0 in place of x for both of those, the inverse tangent of 0 is 0 is equal to c. So my final answer is a -1 to the n, x to the 2n plus 1 over 2n plus 1 plus 0 if you really wanted to. I forgot my series notation at the beginning. Okay, I think we've got it. So I know these are a little crazy, but do your best to differentiate and integrate those.